Welcome to maths class. So today we'll study about Cayley Hamilton theorem. So what does it state? It states that every square matrix satisfies its characteristic equation. So first of all, we'll know about what is square matrix and what is characteristic equation. So square matrix is a matrix of order n cross n, which means it is a matrix with same number of rows and columns. Moving on to characteristic equation, an equation determinant of a minus lambda I equal to 0 is called characteristic equation, where A is given matrix, lambda is a scalar or constant, you can say, I is identity matrix of the same order as that of A matrix. Since now we have learned about square matrix and characteristic equation, we can move towards the proof of Cayley Hamilton theorem. So for proving Cayley Hamilton theorem, we'll let A a square matrix of order n. So its characteristic equation will be a minus lambda I equal to 0, as we have learned. Now let us consider an example. Let A be a given matrix which is equal to 1, 2, minus 1, 2. So A minus lambda I will be equal to 1, 2, minus 1, 2, minus lambda into identity matrix 1, 0, 0, 1. And now it will be equal to 1 minus lambda, 2, minus 1, 2 minus lambda. So now let us calculate its determinant. A minus lambda I determinant will be equal to determinant of 1 minus lambda, 2 minus 1, 2 minus lambda, which will be equal to 1 minus lambda into 2 minus lambda minus 1 into 2, and that's equal to 2 minus lambda minus 2 lambda plus lambda square minus minus plus 2. So it is equal to lambda square minus 3 lambda plus 4. So you can see determinant of a minus lambda's value is a polynomial whose degree is 2. And also we can see that order of A matrix is 2. So we get to know from here that the value of A minus lambda I will be a polynomial in lambda with the same degree as that of the order of the given matrix. Now coming back to the proof, we know that we can write characteristic equation as a polynomial in lambda with the same degree as that of the order of the given matrix. So here the order of given matrix is n, and we can write this characteristic equation as p0 plus p1 lambda plus p2 lambda square plus up to pn minus 1 lambda n minus 1 plus pn lambda n equal to 0, because this is a polynomial in lambda with degree n, and that is the order of the given matrix. Here p0, p1, p2 and up to so on pn minus 1, pn are all scalars, or you can say constants whatsoever. And now we have to prove that every square matrix satisfies its characteristic equation. Now we have got this equation as characteristic equation, and we simply have to prove that the given square matrix A satisfies this equation, which means we have to simply replace lambda in this equation by A. So we have to prove that P0I plus P1A plus P2A square plus up to Pn minus 1 An minus 1 plus Pn An is equal to 0. Since this is the addition of matrices, so we have multiplied P0 by identity matrix, and the result will also be 0, which represents 0 matrix, or you can say nullity matrix. So this is the equation that we have to prove. So to prove this, we proceed as follows. We know an identity that A into adjoint A is equal to determinant of A into identity matrix. Using this property, we can also say that A minus lambda I into adjoint of A minus lambda I is equal to determinant of A minus lambda I into identity matrix. Coming back to the example again, A minus lambda I was equal to 1 minus lambda 2 minus 1 2 minus lambda. Now we have to find adjoint of A minus lambda I, so which will be equal to, so here's the trick. There's a simple trick to find the adjoint of a matrix, of a 2 into 2 matrix, that we have to simply replace these two. Like here will be 2 minus lambda and here will be 1 minus lambda, and simply change the signs of these two. So minus 1, here will be 1, and here will be minus 2. So this is the adjoint A minus lambda I value. 2 minus lambda minus 2, 1, 1 minus lambda. So now this is the adjoint A minus lambda I that we have got, which is equal to 2 minus lambda 1 minus 2 1 minus lambda. So can we write it as 2 1 minus 2 1 and then plus lambda minus 1 0 0 minus 1. So now write this matrix as B0 and this as B1 simply. So now adjoint A minus lambda I is equal to B0 plus lambda B1. Now this is a polynomial with degree 1. Remember that order of the given matrix A was equal to 2, and now adjoint of A minus lambda I is a polynomial with degree 1. So we got to learn from here that whenever the order of the given matrix will be n, adjoint of A minus lambda I will be a polynomial in lambda with degree n minus 1. Again to the proof, order of A was equal to n, so we can write adjoint of A minus lambda I equal to B0 plus B1 lambda plus B2 lambda square plus up to Bn minus 1 lambda n minus 1, which is a polynomial in lambda with degree n minus 1. Because order of the given matrix was n, so we can write adjoint of A minus lambda I as a polynomial in lambda with a degree less. So now we have to simply put the value of adjoint A minus lambda I from this equation to this equation. So now A minus lambda I and the value of adjoint A minus lambda I, B0 plus B1 lambda plus B2 lambda square plus up to Bn minus 1 lambda n minus 1 is equal to determinant of a minus lambda I, which we know is equal to this p naught plus p1 lambda plus p2 lambda square plus up to this pn lambda n. A minus lambda I determinant, its value is equal to this. So now we've got this equal to p naught plus p1 lambda plus p2 lambda square plus up to pn minus 1 lambda n minus 1 plus pn lambda n into identity matrix. Simplifying, we get ab naught plus ab1 lambda plus ab2 lambda square plus up to abn minus 1 lambda n minus 1 minus lambda ib naught minus lambda into lambda square ib1 minus lambda cube b2i and minus up to so on minus lambda n I bn minus 1, and now this total is equal to p naught into I plus p1 lambda I plus p2 lambda square I plus up to so on pn minus 1 lambda n minus 1 I plus pn lambda n I. Let's further simplify this. LHS left hand side. So AB naught. So this is a term in lambda and so is this. So we can take lambda common here and it will become AB1 minus B naught. Remember here I am writing B naught instead of I into B naught because this is the property of identity matrix, that whatsoever matrix we multiply with identity matrix, it will give the same matrix as the result. And since B naught is a matrix, so I into B naught is equal to B naught. So in the same way, there's a term in lambda square and so is this, so we can just take lambda square common and we'll get in the bracket ab2 minus I into b1, it is just simply b1 and then lambda square, and in the same way it will be a term in lambda n minus 1, and so there will be a term in lambda n minus 1 here too. So it will be just a b n minus 1 minus b n minus 2 bracket lambda n minus 1, and then this last term we've got is minus lambda n I into bn minus 1 is simply bn minus 1. So how do we get to know that here will be bn minus 2? By following the same way, since here is b1, b0, b2, b1. So if there will be bn minus 1, here simply will be bn minus 2. So this is the left hand side of the equation. Simply writing this RHS again, p0 I plus p1 lambda I plus p2 lambda square I plus up to pn minus 1 lambda n minus 1 I plus pn lambda n I. So now these two equations are equal, and now one can clearly see that there is a constant term and there is a constant term. There is a term in lambda, there is a term in lambda, there is a term in lambda square, and there is also a term in lambda square. So continuing the same way, we can equate both these equations and their coefficients. So let's do it. Let's first equate the constant terms. AB naught is equal to P naught I, and then the coefficients of lambda, and the left hand side is AB1 minus B0, and on the right hand side is P1I, and continuing the same way, coefficients of lambda square, AB2 minus B1 is equal to P2I, so on, and then ABN minus 1 minus BN minus 2 is equal to PN minus 1I, and then finally the coefficient of lambda, and in left hand side it is B minus Bn minus 1, and on the right hand side it is Pni. Now just look at the right hand sides of these terms. Don't you remember something? What we have to prove is this equation, and it's P0I, which is present here, and then comes the P1A, and here's P1I. So we can just simply multiply this equation by A, and then there's P2A square. So here's P2I, we can just simply multiply this equation by A square, and then there's Pn minus 1, An minus 1, and here's Pn minus 1I. So we can just simply multiply this equation by An minus 1, and at last there's Pn An, and here is Pni. So multiply this equation by An, and then just simply add all these equations. We'll get the left hand side of the equation that we have to prove. I am first of all adding the right hand sides of these equations. We'll get P0I plus P1A, because it will be P1 into identity into A, and identity into A will be simply A. So I am simply writing P1A, and then P2A square, and then so on, Pn minus 1 An minus 1 plus Pn An. And now this is the addition of the right hand sides of these terms after multiplying the equations by these respectively terms. And now this is equal to the addition of these left hand side terms after multiplying by these. So it will just simply become, first of all, it's AB naught. Oh, let me just change the pen so that you can distinguish it properly. AB naught, and then just it's A square B1 minus AB naught, and then there's A square into A B2, it will become A cube B2 minus A square B1, and continuing the same way, it's just An Bn minus 1 minus An minus 1 Bn minus 2, and it is at last minus An Bn minus 1. So this is the equation that we have got at last. And now if you can just concentrate on this, you can see that here's AB naught and here's minus AB naught. So these cancel out. A square B1 minus A square B1 cancel out, and this A cube B2 will also cancel out with a minus A cube B2, which will be present here, and this An Bn minus 1 cancel outs with minus An Bn minus 1, and this minus An minus 1 Bn minus 2 will cancel out with an An minus 1 Bn minus 2, which will be present here. Now we have finally got what was needed. This equation equal to 0. Let me write it again. P0I plus P1A plus b2a square plus up to so on plus pn minus 1 an minus 1 plus pn an equal to 0. So which means that every square matrix satisfies its characteristic equation, and hence the theorem is proved. So hope you like it. Thank you so much.